Yeah. Hi, my name is Grant MacDonald. I'm a postdoc at the University of Victoria. I'm here to introduce the event Antarctica and Greenland, hearing thresholds from different ends. Today we have Chris Stokes, who's professor at Durham University, expert in polar ice sheet dynamics, both in the context of modern climate change and over much longer time scales as well. So,
Thanks very much. Yes, it's good to be here, and I'm going to give a relatively short talk on the response of Antarctica and Greenland to our warming planet, with a particular emphasis on the processes that are taking place in Greenland and Antarctica, and drawing some conclusions about the temperature thresholds at which they might be sensitive. But I always like to start these talks. I'd like to start these talks with some lessons from the past through. And the first of those is that when we look at past records of ice sheet change, we know that their response is highly nonlinear, that they're sensitive to thresholds beyond which ice loss essentially becomes irreversible over decades and centuries. And the regrowth takes thousands of years. So it's very easy to deglaciate ice sheets, but it's much harder to regrow them. And if you see this plot on the left, which was published in a study in Nature a couple of years ago, it's a really nice example of this behavior, because we have global mean temperature on the x-axis there, and you can see 0, and you can see the red line at the top there. As you move up through the temperature scale from 0 to 2 degrees, there's not too much of a change. As you go from 2 to 4, the change starts to increase. As you go from 4 to 6, you really start to fall off the edge of the cliff. And then you come right down to where a global mean temperature of 10 degrees, you've almost completely deglaciated Antarctica, which contains, something of the order of about 58 meters global mean sea level rise. Then as you, in these model experiments, as you cool temperatures, you don't go back up the same way. You actually climb back up that curve, a slightly different route. You take the lower red curve, and this behavior is known as hysteresis. What it actually shows you is that for any given temperature threshold, you have a state of Antarctica in a deglaciating phase, and then a state of Antarctica to regrow it, which actually requires you to cool it more and more to get back to that state. So actually, if we do deglaciate Antarctica and we wanted to put it back together in its entirety, we'd actually have to cool temperatures below present day. And another reason I like this graph is that it kind of gives a sense as temperatures increase, we might see only small changes, but then they'll get rapid. So it's almost like we're stood on the top of a cliff and we're walking toward the end of that cliff at the moment when it comes to ice sheets and their contribution to sea level rise. And the colour here of nature points out that we're rapidly approaching the point of no return. The other thing about this paper is that actually it suggested that the West Antarctica actually had a threshold of around 2 degrees and East Antarctica was about 6 degrees. And even just in a few years, I would say that science has changed and that the West Antarctica actually threshold has come much further to close to 1.5 and possibly East Antarctica probably to less than 2 degrees. So that's the first lesson from the past, is that ice sheets can seem to be doing very little, but then very rapidly change and contribute to sea level. And the other lesson related to that is that we know from past records that sea level rise can actually be 10 times faster than present due to a number of self-reinforcing feedback mechanisms. So on the left-hand side here is a plot of the North American Laurentide ice sheet, deglaciating at the end of the last ice age between about 20 and 10,000 years ago. And you can see on the right-hand side here, the post-glacial sea level rise. So when we had the last glacial maximum about 21,000 years ago, we know sea levels were about 130 meters lower. And as this ice sheet deglaciated, you actually see sea level increase, but it doesn't do so linearly. In fact, it does it in little jumps. And there's one famous jump that's been studied quite a lot called Meltwater Pulse 1A. And we know from studying the records of Meltwater Pulse 1A about 14,500 years ago, that sea level could have increased 4 meters per century. That's 40 millimeters per year, i.e. 10 times quicker than the current rate, which is just less than 4 millimeters per year. So 2 lessons from the past on that ice sheets seem to be doing very little and then all of a sudden respond. And then when they do respond, they can lead to rates of sea level rise that are much, much higher than we're observing in the present. So I'm just going to give you an overview of Greenland and what the observations say, and then what some of the future projections say. So first of all, Greenland ice sheet stores just over 7 meters sea level equivalent. You can imagine during winter time, it gains mass as snow falls over the entirety of the ice sheet. And then during the summer, it loses mass by two processes. About 50% of its mass loss is via melting in the surface. The other 50% is what's known as dynamic discharge. This is the ice pulling down, or the ice flowing, drawing down that ice snow from the interior, and then carving icebergs into the ocean, which obviously also contributes to direct sea level rise. And this map of Greenland is showing you the ice speed in meters per year, where those dark red colours are velocities of around 250. We know some of these glaciers flow at several thousand meters per year. So they're pulling down that ice and discharging it into the ocean. And at the moment, when you measure the amount of snow that falls and you measure the amount of ice that's lost by melting and dynamic discharge, we know that mass loss far exceeds mass gains. And there's been a marked increase in particular in melting in recent years. So this figure shows in the blue line the typical or the median melt extent in Greenland through a seasonal cycle over the last, well, it's from 1981 to 2010. And what you can see is that it usually reaches a peak around June, July, but also you can see the interdecile and interquartile ranges. And then in the red line, you can see this last year, 2023. And you can see that the melt extent for Greenland now has far exceeded what we've observed in recent years. And we also know that in some years in particular, almost the whole of the ice sheet now experiences some summer melt. And there's been some nice work we've done recently showing that effectively this ice sheet is now so far out of equilibrium with the current climate that we're probably already committed to almost 30 centimetres of sea level rise without any further warming. That's really just as the ice sheet in its current state catches up and equilibrates to the climate in which it now sits. So if we look at the mass balance records of Greenland, we know that it was last in balance in the 1980s, possibly early 1990s, when CO2 was around 300 parts per million. And we now know that obviously CO2 is just exceeding 420 parts per million. And since the early 1990s, Greenland has lost nearly 4,000 billion tonnes of ice and has added 11 millimetres to sea level rise. You can see some of the kind of spatial extent of the mass loss in this animation from the GRACE satellites. So the red colours that will emerge on this figure are showing you the parts of the ice sheet that are losing mass at the highest rate. So actually, early on in the record, it was mostly restricted to coastal regions. But what you'll see here, as time passes, and this is 2010, and we'll go through to 2023, what you can see is that mass loss, that zone of mass loss, is actually encroaching really up to quite high elevations in Greenland now. And so it's really quite worrying that the mass loss in Greenland appears to be accelerating. It contributed 0.7 millimetres a year to sea level rise to 2018. But if we look at the last few years in Greenland, well, we've had some really hot years, as we know from the global temperature record, which of course is amplified in the Arctic regions. If we look at that in a bit more detail, you can see the mass loss there in the black line. The observations now show that in the last few years, it's actually increased to 1.2 millimetres per year. What's interesting about that number is it actually sits above the upper range that was predicted by the IPCC report just a few years ago. So the IPCC made some predictions a few years ago. We've now had some recent observations and we can compare the two. And the black line here is sitting right at the upper limit of the worst case scenario. And if this continues, Greenland will add at least 20 centimetres to sea level by 2100. And of course, it could also accelerate slightly above that. Longer term projections of the ice sheet are actually fewer and further between. We tend to focus on 2100, but there are some very valuable studies that extend that temporal range. And longer term projections give a sea level rise from Greenland of somewhere between 0.7 and 1.9 metres, and that's under the 2.6 scenario. So, that's something that, we're certainly we're on track for at the moment. And I think this is often lost, and even these low emission scenarios, we are committed to losing mass from the Greenland ice sheet. Of course, if we go to higher emissions, something like RCP 8.5, which hopefully we've dipped under, and we won't go on, but we're looking at 5 meters to almost complete deglaciation of Greenland over a kind of 2,000 to 3,000 year time scale. So this is really quite worrying here, that I think Greenland effectively is not where south of people often think, and it's very vulnerable to the warming we're seeing in the Arctic. I'll now move on to Antarctica before summarising some of the impacts of sea level rise. Now, the Antarctic ice sheet actually stores far more than Greenland. Antarctica actually holds about 58 meters of sea level equivalents. About 5.3 meters of that is in West Antarctica, with the rest in East Antarctica. So by far the world's largest ice sheet is actually the East Antarctic ice sheet, which has so far been really neglected, I think, in terms of its study, but which is attracting a lot of attention at the moment. Much like Greenland, Antarctica gains mass through snowfall, but there's much larger interannual variability. So in Greenland, there is interannual variability, but there's a predictable seasonal cycle. In Antarctica, there's the seasonal cycle, but there can be some years where snowfall, is way outside the kind of average range. Unlike Greenland, there's very little surface melting. And this is important because most of the mass loss in Antarctica is actually being caused by ocean currents that are thinning the floating portions of the ice, and they're causing this dynamic discharge. So most of the losses from Antarctica is via dynamic discharge, ice calving, and melting from warm ocean currents. Mass loss via those processes far exceeds mass gain to the West Antarctic ice sheet. But interestingly, the East Antarctic ice sheet appears to be in balance, albeit with much larger uncertainties because of those large amounts, that large internal variability and so forth. So if we look at this plot again, it's got Greenland on in blue, which I showed you a few minutes ago, which has been the dominant ice sheet contribution to sea level rise. The green plot here is showing West Antarctica, which has had about 7 millimeters to global mean sea level rise in recent decades. And if we look at East Antarctica in orange at the top there, it's kind of bumbled along around about 0. There are some people think it's losing mass. There's other studies suggesting that it might be gaining mass ever so slightly. Broadly speaking, it's been in balance. So compared to Greenland, the West Antarctic ice sheet was also close to balance in the early 1990s, but has also started to lose mass since then, contributing around 7 millimeters to sea level. And we know it's been driven by real ocean currents rather than surface melting. So the same plot for Antarctica, again, this is from satellite records that are effectively weighing the ice sheet beneath them, really gives you a really clear focus of where the mass is being lost. And you can see emerging quite strongly is the mass loss in West Antarctica, around the Andalusia embayments, where we know warm water is coming up onto the continental shelf. They're weakening some of the floating ice shelves. They're removing, they're causing to break up, and there's been an increase in the discharge of these glaciers through time. What I think is really interesting on this plot is that we're starting to see emerging signs of mass loss in the East Antarctic ice sheet, particularly in this region here, known as Wilkes Land. And we've also got evidence that the waters off Wilkes Land have also been warming recently, and probably also melting some of the floating sides of the glacier, the other side of the glaciers in Wilkes Land. So we're seeing the same processes emerging in East Antarctica that we've been observing for a few decades now in West Antarctica. And in terms of what this actually looks like on the ground, so to speak, this is from a satellite image, but I think it's a really nice impression. This is Pine Island Glacier from the West Antarctic from that area of mass loss. And this is just showing you a few satellite images over the last few years. And we're seeing the floating zone retreat, a breakup. This, we think, mostly due to warm ocean currents getting into the cavity underneath this floating part of Antarctica. Now, I mentioned Wilkes Land in East Antarctica, and I think it's really important to draw attention to this because a recent study suggested that mass loss in Wilkes Land is now 10 times higher than it was a decade ago. So this same kind of satellite data just a couple of decades ago showed no signs of mass loss. And all of a sudden, in the last couple of decades, we've started to see these hotspots emerge in East Antarctica. And the thing that's really interesting about this is that it shares many characteristics with the West Antarctic ice sheet. It's kind of like a mini West Antarctica embedded within East Antarctica, because the better relation map shows that, like West Antarctica, it's grounded on land that's below sea level, which makes it particularly vulnerable to instabilities. As I said, we know that off this part of Antarctica, a recent study has shown that the circuit polar deep water that travels around Antarctica has warmed from about 0.8 to about 2 degrees C since the 1990s. And we now know from some of the work we've been doing on a glacier in here that actually the fastest rate of grounding line retreat was detected, or the third fastest grounding line retreat in Antarctica, that junction where the ice begins to flow, is actually now found in Wilson. We tend to associate rapid grounding line retreat in the West Antarctic ice sheet, but we're now starting to see comparable rates of retreat in East Antarctica. So I'm a little bit concerned now that the East Antarctic ice sheet is also starting to respond to ocean warming. Before I just look at some of the sea level projections from Antarctica, I think it's really important to recognise two possible instabilities that could lead to very rapid rates of sea level rise, similar to the rates that we've seen in the past. One of these is known as marine ice sheet instability, and one is known as marine ice instability. Now, marine ice sheet instability takes place when the bed of the ice sheet slopes downwards and gets deeper as you travel inland, because once you push the glacier, the bit where the glacier begins to float into deeper and deeper water, it has to discharge more ice to try and stabilise that position. And of course, it won't stabilise until it's either gripped very strongly by a narrowing constriction at the sides, or it finds higher ground on the seafloor, which will slow down retreats. And marine ice sheet instability was known about in the 1970s. It's theoretically very robust. We know it should happen, and the situation in which it should happen. And actually, some people have suggested that this process has actually already started in West Antarctica. That busy was already underway, maybe as long as 10 years ago. And potentially what that means is that it will be irreversible, irrespective of how ocean climate changes in the future, the ocean climate changes in the future. Now, obviously, models are increasing in their sophistication year by year, and the latest work that specifically looked at this problem of irreversibility suggests that it's not yet irreversible, that it can be reversed, but that if sustained, if current climate is sustained at whatever it is, 1.1, 1.2 degrees warming, then it will lead to slow and irreversible retreats over the next few centuries. And they called that in this paper committed tipping. So this is kind of suggesting that actually West Antarctica, even present day forcing, if it's sustained, would be enough to tip it into a reversible retreat. And of course, that's also significant. We've had recent studies showing that there's been dramatic ocean warming. So it's unlikely that we're going to be able to sustain them. Now, the other instability is known as marine ice cliff instability, and this involves the rapid removal or collapse of ice shelves that float. So if you get rid of them, you're exposed quite deep cliffs at the grounding line, which then collapse like kind of coastal cliffs. They're undermined by the water and they topple into the ocean. And of course, as you start that process, you expose a higher and higher ice cliff. So again, it can become a runaway feedback. And we know that this is not yet underway, but we do know that this is something that could happen if we start to rapidly remove some of the ice shelves around Antarctica, either due to ocean warming or atmospheric warming. And so this is something that we're really going to have to keep an eye on, I would say, over the next few years. And recent modeling shows that under high emissions and with this marine ice instability, you can actually get catastrophic sea level rise very, very rapidly from Antarctica. And the latest IPCC report was unable to rule out some of those high-end predictions. So this is a very influential paper that was published a couple of years ago, showing the difference between limiting warming to 1.5 versus moving beyond that. So with warming limited to 1.5, this is what these plots show. And you can see from these plots that by 2300, we'll be looking at about a metre of sea level rise. And at 2100, it would maybe only be about 10 centimetres of sea level rise. So if we can limit temperature increases to 1.5 degrees, I think we're looking at a slow and steady, but nevertheless an increase in sea level from Antarctica. Current policies, i.e. about 3 degrees of warming, give around 1.5 metres at 2300. That's what you can see on the bottom left of there. A high emission scenario would give around 10 metres at 2300. And as I said, these were figures that are quite alarming, but which the IPCC were unable to rule out. And the other thing to notice on particularly the bottom two curves is that you don't really see Antarctica responding. You know, we may exceed 3 degrees potentially in the next few decades towards the end of the century. You don't see a response at the same time scale. There's a delayed or a lag response, and then we really start increasing sea level, which I think is very worrying. So this is the plot from the IPCC report that goes through the different scenarios, and then they've added in the dashed line there. And they're very clear that projections in which Antarctica contributes much more than those assessed ranges, the lower part of the graph, but the sustained very high greenhouse gas emissions, equivalent to 7 to 14 metres sea level rise by 2300. And again, I always point out that even the low emission scenarios could give you over 3 metres at 2300, which is kind of like this bar here showing the sea level rise from those high emissions 2300. I've mentioned sea level rise a lot. I'm just going to finish up by making the point that sea level rise in the global mean sea level that we've been talking about, it masks regional variation. So if you were to look at the period 1992 to 2019, the average sea level rise was about 3.3 millimetres per year. But the red colours here are showing you parts of the world that would have actually, due to gravitational effects, would have actually exceeded 5 millimetres per year. These kind of headline numbers like global mean sea level, they also ignore the impacts of storm surges, and they also ignore the impacts of land subsidence in some of the major coastal cities, and in some cases uplift, which also means that we really need to be thinking about relative sea level rise. There's also been some recent work that specifically looked at how AOC stations, the Alliance of Small Island States, could experience somewhere in the region of 11 to 33% higher sea levels than the global average, simply due to the gravitational effects. And the darker colours on this world map are showing you where sea level rise is amplified above that global mean. And I think it's worth remembering that globally, around about 230 million people live within a metre of sea level. And that's something that I think is becoming more and more likely, potentially by the end of this century. And 1 billion people live within 10 metres of sea level. There's also been studies looking at the kind of economic costs of associated with flood losses, 20 centimetres of sea level rise, so certainly something that we're pretty much committed to already, I think, over the next few decades, leads to annual flood losses of $1 trillion for the world's largest coastal cities. There's an example here from Northwest Europe, and I have another example here with 3 metres of sea level rise within Florida and some of the Caribbean islands as well. So to conclude, I think the science, both observations of ice sheets and of sea level, but also the modelling, is advancing really rapidly and actually much more quickly than IPCC experiments. So the next IPCC report won't be probably 27 to 2028. And actually, the science, even what we've discovered in the last 2 or 3 years since the last IPCC report, is showing that things are actually worse or are likely to get worse than predicted. There are very few studies out there that bring good news on this subject, I'm afraid. The combined ice sheet contribution to sea level rise is now 4 times higher than it was in the 1990s when the ice sheets were last in balance. And so just a very simple comment that suggests that if we want to stop sea level rise on ice sheets, we need to go back to where we were in the 1980s, where we had carbon dioxide concentrations of about 350 parts per million. Both Greenland and West Antarctica, I think it's becoming pretty clear now, will take decades to adjust, even if we just keep current forcing as it is. There is a committed sea level rise. Potentially that commitment could be several metres, but very, very slowly, if we stick to current climate forcing. But it could also get irreversible retreat much more quickly if we start to approach 1.5, and certainly if we start to exceed 1.5. So the latest science, and there's been several papers recently looking at specific thresholds for some of these systems in the Earth, including Greenland, including West Antarctica, including the marine bases of East Antarctica. And they all show that exceeding 1.5 will almost certainly trigger irreversible retreat of Greenland and the West Antarctic Ocean, likely to reach several centimetres of sea level by 2300. The East Antarctic Ocean is currently imbalanced, but there's clear evidence there to suggest that some parts are losing mass, driven by the same process we're going to see in West Antarctica. And there's a real concern that if we were to exert 2 degrees C, then we would awaken that sleeping giant in the southern hemisphere. So I'll finish there. Thanks very much.